Hi, thanks for joining me. Today I've got a pretty interesting video. This problem was sent to me by a viewer, so shout out to Rob for sending this through. And this is from a 1934 Canada maths exam. And this exam was for students looking to get scholarships to study maths at university. And I've taken question 2 from this paper because it was, well, sent to me as an interesting problem, and I had a go at it. And I have got a solution, and there's no mark scheme for this paper, so I don't know if my solution is the intended solution. And I suspect that there is a slightly more elegant way to solve this problem. So I'll be intrigued to see what you guys come up with when solving this problem. What is this problem? We are asked to show that if a, b, p, and q are real numbers, then so are the roots of this equation here. So a squared over x minus p plus b squared over x minus q equals 1. So this is obviously an equation. It doesn't look too bad to deal with, and we're told to say that, or told to show that this guy here has real solutions if a, b, p, and q are real numbers. Now, one thing I noticed is that, well, if a and b are both 0, then these terms are both 0, and so it doesn't add up to 1. So I imagine there's a small typo here in this question. So we're going to insist here that a and b are both, or at least one of them is non-zero. So in other words, a squared plus b squared is bigger than 0. If you want to have a go at this problem, pause the video now and give it a go for yourself. And I'm going to go through a solution, but I'm going to present it in the way that I kind of came about it. So I'll talk you through my thought process. So hopefully it should be slightly different to normal, and you get to see what my thought process is to solving these sorts of problems as a mathematician. So my first thought for this problem, which is what I imagine your first thought was, is let's just cross multiply here and see what we get. And you get a squared times x minus q plus b squared times x minus p equals x minus p multiplied by x minus q. And cool, this is just a quadratic, right? Let's just expand everything. So we get a squared x minus qa squared plus b squared x minus pb squared equals x squared minus p plus qx plus pq. Okay, cool. Let's just bring everything onto one side. So the x squared stays there. And now this x term, we've got minus p plus qx, but if I bring the a squared and the b squared over, I get minus p plus q plus a squared plus b squared x. And then what's my constant term? Well, it's going to be pq plus pb squared plus qa squared, like so. Cool, this is a quadratic, and we want to show that this has real roots. So surely we can just show that the discriminant is positive. But oh my goodness, that would be horrendous to try and show here. The discriminant would be this thing squared minus 4 times 1 times this thing here. And that would involve so many letters, so much algebra, and there's so much potential to make an algebraic slip and make a mistake. And it's just not elegant. So it's probably not the intended solution here. So I kind of gave up when, or kind of just, said, right, this is probably going to lead to a dead end. Let's not go this way. So back to the drawing board. So my second thought here was, well, let's look at these a squareds and b squareds. That's slightly suspicious. Why have they put a squared and b squared there as opposed to just a and b? Maybe that's got something to do with the fact that a squared and b squared we can guarantee are non-negative. But at the start here, it's not really clear how we can use that, but that's just something to bear in mind, that we're probably going to have to use the fact that the numerators of these fractions are guaranteed to be non-negative. Okay, so next thing I thought was, well, do something that mathematicians like to do with problems where they're not really sure where to go, is just fiddle about, play about with this, ask yourself what happens in certain scenarios. So, well, what happens if P and Q are the same? Well, if P and Q are the same, we have that this thing on the left-hand side can just be written as a squared plus b squared over x minus p is 1. And this just rearranges to x is p plus a squared plus b squared. And this, of course, is clearly a real number because p, a, and b are all real numbers. And so this is definitely a real solution. And so that proves that if p and q are the same, this equation does indeed have real solutions. And so that bit's done. So now we can assume from here on that p and q are distinct numbers. So we're assuming p does not equal q. And so therefore one of the numbers out of p and q is bigger than the other. And because of the symmetry of this equation here, we can just assume that, P is less than Q. So from here on, we're going to assume, without loss of generality, that P is less than Q. Now, here's the trick. What we're going to do is do a bit of a translation on this left-hand side. So let me just write it out in a bit of a weird way. I'm going to write this as a squared over x minus q plus q minus p. And then this is going to be just b squared over x minus q equals 1. So all I've done is I've written x minus p as x minus q plus q minus p, like so. And now if I just call this left-hand side here, f of x, the thing is, if f of x equals 1 has solutions, I mean, I could sketch this graph, but let's just, for argument's sake, say it looked like that. And the graph, the line 1 is there. Now, if I take this graph and just horizontally translate it, that is not going to impact the number of real solutions. So if I take this yellow graph and I horizontally translate it, it does not change the number of real solutions. So this yellow one had 3 solutions, 1, 2, and 3, and so the orange one would also have 3 solutions for when I make it equal 1. And so that tells me that if I do a horizontal translation on f of x, that's not going to impact the realness of the roots. And so all I've got to do here is do this little transformation of x minus q. So in other words, all I'm going to do is subtract q from my solution. So essentially, we can reduce the problem to a squared over x plus q minus p. And I'm just going to call q minus p, let's just call it delta. And delta here is a positive number, and that will be important in a moment. So a squared over x plus delta plus b squared over x equals 1. So just to go over that, all I've done here is I've basically, if you want to, I can call this capital X, maybe make it a bit clearer, and I'm just saying that capital X is simply x minus q. And so now I'm just looking to see if this equation here has solutions for capital X, or real solutions for capital X. And now what I'm going to do is cross multiply this and kind of do what we were initially thinking to do. So this would be a squared x plus b squared x plus b squared delta equals then x squared plus delta x, like so. And now this is a little bit prettier than the initial quadratic that we had when we just kind of, put our head down and just cross multiplied here. This is slightly more strategic. And now what we can do is put this as x squared plus, and now if I bring the x terms on this side, this will be delta minus a squared minus b squared times x, and then minus b squared times delta equals 0. And the magic of this happens here. So minus b squared times delta, we know that delta is a positive number and b squared is non-negative, and so this thing here is guaranteed to be less than or equal to 0. And this is a positive quadratic because there's a 1 there. So we know that the y-intercept of this graph is some negative number, or a non-positive number, minus b squared delta. And so in order to sketch this quadratic, maybe it looks something like this, or maybe it looks something like this. I don't know. To be honest, I don't really care that much. I just care about the fact that it must cross the x-axis at 2 points, and therefore it has 2 real roots. So capital X has 2 real roots. So if I just add q to those roots, that's going to give me lowercase x, which is still going to be a real number. And so therefore my equation here is guaranteed to have real roots. So this is my solution to this problem. I'm not sure. There might be a slightly easy way to do it. I don't know if this doesn't seem super elegant, but it does seem more elegant than kind of just cross multiplying. So do let me know if you can think of a slightly nicer way of doing this. I think maybe you could get away with doing some sort of calculus here, but I haven't really explored any other options. So I'd be intrigued to see what your thoughts are. And if you have enjoyed this problem, thankfully Ron sent me a bunch of other problems from this exam and set of exams. So let me know if you'd like to see me tackle some of the other problems as well. Anyway, thanks so much for watching. If you're new to the channel, please do give this video a like and subscribe if you haven't already. As always, have a lovely day, and I'll catch you in the next one.